This is a good
Welcome to the thermal runaway testing video brought to you by the Eagle Flight Research Center. As we push the boundaries of aviation technology, one of our key focuses is enhancing the safety and efficiency of lithium-ion batteries, specifically the 18650 battery packs used in various aviation applications. The 18650 lithium-ion battery is popular in the aviation industry due to its high energy density and efficiency. However, these batteries can pose safety risks due to thermal runaway. But what exactly is thermal runaway, and why is it so dangerous? Thermal runaway occurs when a battery's internal temperature and pressure escalate rapidly, leading to a self-sustaining chain reaction. This can be triggered by factors such as overcharging, physical damage, or manufacturing defects. The structure of an 18650 battery, commonly used in everything from laptops to electric vehicles, makes it particularly vulnerable to this issue. These batteries are compact and powerful, but this energy density comes with increased risks. As the battery heats up, the chemical reactions inside accelerate, which in turn generates more heat. If the heat can't escape quickly enough, or if the temperature reaches a critical point, the battery's materials can break down and release gases. This breakdown can cause the battery to catch fire or even explode. The release of toxic gases and the potential for flying debris make thermal runaway a serious hazard, not just to the device but to users and their surroundings. Through thermal runaway tests, we can determine at what point the battery fails and use this data to enhance battery design and safety protocols, ensuring the batteries are safer for everyday use. At the Eagle Flight Research Center, we are researching experimental techniques to mitigate the risk of thermal runaway. One promising approach involves the use of sodium polyacrylate, a superabsorbent polymer, as a thermal barrier. When applied to battery packs, sodium polyacrylate absorbs and retains large amounts of heat. In the event of a temperature spike, this material is released from its bag and forms a gel-like barrier, insulating the cells and slowing down heat propagation. This not only helps in managing the battery's internal temperature, but significantly reduces the risk of thermal runaway. Our ongoing experiments aim to integrate this technology into the battery packs without compromising their performance. The goal is not only to prevent thermal runaway, but to ensure that our battery systems are robust enough to withstand the unique challenges of the aviation environment. The FAA's rules for 18650 battery packs are that the batteries, when undergoing thermal runaway, must not have ejecta, fumes, or flames exiting the packs in a way that would harm the pilots or passengers. To gather control data on Sanyo 18650GA 4.2 volt 3.5 amp hour lithium batteries experiencing thermal runaway as a part of an experimental fire mitigation technique employing sodium polyacrylate hydrogel. This includes determining if the current interrupt device, or CID, which is located at the positive end of the battery, will activate well before any thermal runaway event occurs. Using thermocouples, we are able to monitor the temperature while the batteries go into thermal runaway, as well as how hot they get afterwards. A welding fume scrubber was placed above the container to remove smoke from the thermal runaway. There was also a large fan placed at the other end of the test cell, blowing air through to clear the smoke. To force the batteries into thermal runaway, the battery is wrapped with 24-gauge nichrome wire and is plugged into a power supply capable of delivering 30 volts at 10 amps, heating the wire. The setup includes a clamping jig inside of a steel container with thermocouples and cameras placed around the container to record data. All batteries in this experiment were charged to 100% state of charge. In the first test, current was applied starting with 1 amp and rising to 4 amps with the intent of finding the lowest possible current that would force the battery into thermal runaway. During the thermal runaway event, a sidewall rupture was observed. The team speculates this could be due to rapid heating of the cell wall. Based off the observations of test 1, the power supply was set to 2.5 amps for the remaining tests. A sidewall failure still occurred. The second test shows the cathode rod starting to leave the battery, potentially ejecting the nail-like object. Tests 1 and 2 are the only tests to experience sidewall ruptures. Both sidewall ruptures occurred towards the positive end of the battery. In research documents related to thermal runaways of 18650 batteries, sidewall ruptures are rare but do occur under certain circumstances such as excessive heating to the cell wall. The team sought to find the minimum temperature needed for the thermal runaway in Test 3. The full test took over an hour, with the battery being above 200 degrees Fahrenheit for 25 minutes. The heater was cycled multiple times throughout the test until the thermal runaway initiated. Here, the signs of thermal runaway are a constant flow of smoke from the positive end of the battery and a steady increase in temperature after external heating is removed. Improper timing allowed for the test article to slide out of the test jig. All contents of the battery were expelled out of the positive end, including the cathode rod. A large quantity of smoke was observed during Test 4, causing the team to shut off the heater early. The team surmised that the thermal runaway had not begun since the temperature did not increase on its own, which is the second indicator of thermal runaway, as observed in Test 3. The heater was turned back on and the test was resumed. The battery experienced a typical thermal runaway. The procedure did not change after this point. Test Article 5 was not properly timed when assembled, resulting in the fracture of the FR4 PCB when the runaway event occurred. The test article escaped the jig and expelled all of the material inside of the battery. Future test articles use a different wire tying technique to reduce the possibility of this event occurring again. This included twisting the wires above the FR4 PCB as shown. This reduces stress on the PCB and allows for proper tightening. Updates to the test jig are being added for multi-cell tests to secure the articles better. Trials 6 through 10 were the second day of testing and included all of the tweaks that were made to the test card from the first day of testing. Test 6 was a successful thermal runaway, yielding consistent results to the previous tests. During Test 7, a bucket failure occurred when the safety pin retaining the bucket was prematurely triggered, causing pellets to be dumped onto the battery. Because the battery had reached 200 degrees Fahrenheit, we had to wait for 10 minutes to let the battery cool to a safe temperature before removing the fire retardant pellets, resetting the test. The battery was then forced into thermal runaway as a safety precaution, but the data was not usable. The blue glow observed in the 18650 batteries is a result of incandescence, which is the emission of light from a hot object due to its high temperature. Incandescence typically starts with a dull red glow at lower temperatures and progresses to brighter colors as the temperature increases. At extremely high temperatures, the glow can shift towards blue. Incandescence occurs when an object emits electromagnetic radiation due to its heat. Test 8 was a successful thermal runaway, yielding consistent results to the previous tests. Test 9 was a successful thermal runaway, yielding consistent results to the previous tests. Test 10 had a thermocouple issue which read considerably lower temperatures than the cell wall thermocouple was reporting. That data has been excluded and the cell wall thermocouple will be used as the main data point. Test 10 was a successful thermal runaway, yielding consistent results to the previous test. The cathode rod once again was protruding from the battery. A chart of all of these successful trials were compiled, illustrating the temperature range at which these batteries go into thermal runaway. A large range was observed, with the lowest temperature recorded to achieve thermal runaway being 198 degrees Fahrenheit, while the highest was 265 degrees Fahrenheit. Across all tests, the CID had ruptured well before the battery had reached thermal runaway, and when heating is removed prematurely, the battery temperature reduced at a constant rate and did not enter thermal runaway.